হ্যাঁ,
তুই
রেকর্ড অন দিস
দেখে
কম্পিউটার স্টার্ট হয়ে গেছে। ঠিক
তাই
আছে,
না, রেকর্ডিংটা এখন বন্ধ করে রাখ।
আমি টেস্ট করছিলাম যে
শোন।
কিভাবে হচ্ছে। I think we can at least start with the introductions right now. It's 11:37. What do you say, Pratap?
Yes, sure. You can start.
Okay. Okay. So once again, good morning, everyone. Welcome to the fifth talk in this series of Journal Club Talks in Condensed Matter Physics of TIFR. So for today, we have the speaker with us, Pratap Chandra Adak. So his introduction would be like he completed his bachelor's from Ramakrishna Mission Residential College at Narendrapur. After that, he joined the MSc Physics program in the Indian Institute of Science in Kanpur, which he passed out in 2016. After that, he has been continuing his PhD studies from Tata Institute of Fundamental Research, working in the nanoelectronics group in the Department of Condensed Matter Physics and Material Science, under the guidance of Professor Mandar Deshmukh. His area of research would be to study the electronic properties of various two-dimensional materials, graphene being his like primary aspect of work, and the electron transport and various studies that he will tell about in his talk. So apart from his academic introduction, he has like interest in computers and programming, and his special interest lies in automating various tasks for his lab. So without much further delay, it's over to you, Pratap.
Yeah, thank you so much. So I was a bit overwhelmed with this introduction because this is first time someone is introducing me for before a talk. So anyway, and a big thanks to the organizers as well. And so they have arranged these things, and this is already I think fifth week, and this is a great like this is very good arrangement in our department. And I also talked with many people to start something like this, but yeah, thanks to them. Anyway, I have a confession one here, so let me share the screen first. Yeah, so I have one confession is that this is my first week in journal club, because first time I could not wake up at time to join the talk, and then I have a more valid reason that I went home. So I really don't know what type of audience I am expecting. So in this kind of thing, I have two default settings. One is when there are professors and I try to unsuccessfully pretend that I have some bit of knowledge, and I try to prove that. But another settings is when some new student or some like not so much expert are visiting our lab, and they want to know what interesting things we are doing. And in that case, I try to pretend that we are having much fun doing experiments, while deep inside us we all know what is PhD. So anyway, I am going to take this second default setting. So the bottom line is, please ask whatever question you want, and I really don't intend to make the talk theory heavy or like too much nitty-gritty details, but my intention is that to give you sort of overview of what we do and how we do. So of course, please ask any question. And so now, before going to the actual talk, I just quickly visit our lab website. So this is sort of the type of research we do in our lab. In our lab, there are lots of instruments and there are lots of people, and we do different kind of things. So in one case, we do transport, electronic transport in 2D materials, which I am also involved in. And so here we basically make a nanoscale device, like 2D material based. One of the 2D materials we use is graphene. There are MOS2, WC2, and CGT, whatnot, like different kind of ferromagnetic material. And we basically put some contacts and then measure some resistance, and then analyze the data and talk big things. But another subgroup is there, they talk about nanomechanics. So basically this is one image where they make nanoscale drum, micron scale drum of graphene, and they basically like what drummer do. So they basically give some mechanical vibration in the drum, and they try to analyze what is the mechanical properties, resonance things. And some other people like Sanat, they are exploring 2D superconducting material like Bisco. And there are other type of instrument where we can explore optical properties as well in our lab. Right now, our major focus is not in that direction. But yeah, so there are different kind of work we do in our lab, and my primary work involves electron transport. So now let me present what I wanted to present. So so as I put in the title, I am going to talk about twisted double bilayer graphene, electron transport in twisted double bilayer graphene. So we have two recent paper. One is in Physical Review B, and another one is in Nature Communications. And I will mainly talk about those two papers, but they are like in the last 6 slides only. But before that, I will give you a broad sort of perspective on twisted bilayer graphene. Then I will give an introduction to twisted double bilayer graphene, and then I will talk about these two work. One is on T-Nobel bandwidth and gaps in twisted double bilayer graphene, and another one is on bulk valley transport and Berry curvature physics in twisted double bilayer graphene. So so let me first yeah so so let us go to our undergraduate course and take a quick recap on what is the effect of periodicity in a lattice. So this is basically just a near electron free electron gas model. So you have a quadratic band structure of free electron gas. Now the question is, if you are talking about periodic lattice, what happens? So basically we know that you have to consider the effect of periodicity. You will get Brillouin, and in the momentum space, if you plot the energy dispersion, you have to basically put copies of this original energy dispersion, which is quadratic. Now if you turn on the crystal potential, you will see that where two sort of neighborhood energy dispersion are crossing each other, you will open up a gap if you turn on the crystal potential. and eventually what you will get bands. And this is right side is basically different way of representing the band. So basically, due to periodicity, you are getting band structure, and that means periodicity does some magic. So this we will keep in our mind, because it will be helpful to understand what twisting does in graphene system. So let me first now quickly tell you what is graphene. I think everybody knows that graphene is basically a sheet of carbon atoms, and which is decorated in hexagonal pattern like this. And this is graphene is basically one layer of carbon atom. So if you take graphite, which is one form of carbon, so this graphite is basically made of this kind of layers, and interlayer attraction between these different layers are very small. So that's why you can actually exfoliate and actually take out one single layer and put that on some substrate, and that is basically graphene. Now, of course, physicists are always go into momentum space. And for graphene, the Brillouin zone is also hexagonal, and in the Brillouin zone there are many symmetry points. One of them are this K and K prime, and other one is gamma and M. So K and K prime is actually called valleys in graphene system, because if you calculate the energy dispersion, I have represented one picture here. So can you follow my mouse? Anyway,
Yes,
I think
yes.
you can
Pratap,
follow. Yeah.
yeah, we can.
Yeah, you can follow my mouse. Okay, yes, thank you. If you calculate the energy momentum dispersion, you will see that uh, the conduction band and valence band, they touch each other at some particular symmetry points, which are these K points. Now if you zoom in there, because in most of the experiments you will access only low energy spectrum, so basically you will explore this small area, and there you will find that energy is linearly proportional to the momentum if you count momentum from this K and K prime value. So for graphene system and for any other similar 2D hexagonal lattice structure, we talk in terms of values, these K and K prime values, and when we only talk in the energy scale neighborhood of these values. So for us, graphene is basically this kind of system where energy is linearly proportional to momentum. And if you remind yourself about Dirac materials in quantum mechanics, if you know that for the Dirac particles also energy is proportional to momentum. In that case, the proportionality constant is the speed of light. But in this case, the constant is not speed of light, but much less velocity, which is called Vf, and that is sort of 100 times 10 to the 6 meter per second. So that is much larger than the speed of light, but the Hamiltonian structure is very similar, and that's why graphene is very interesting from the theoretical perspective. And for us, graphene is basically this kind of cone where you have electrons filled up to zero energy. Zero energy is this point where sort of conduction band and valence bands is touching each other. Now, what you do, you take these kind of graphene sheets and put these on a substrate like SiO2 coated Si, and you put some electrical lead, and you basically measure voltage, send current and measure voltage. So you basically measure resistance. And but there is one interesting thing in graphene, like any other 2D materials, that you can change the Fermi energy by gating. So for gating, what we do, we put some voltage on this silicon. Silicon is actually highly doped, so effectively that is sort of metal, and silicon oxide here is a dielectric. So you have graphene, dielectric, and a metal. So you can consider that as a capacitor. So if you put some voltage in the silicon, highly doped silicon, you are basically putting some charge on the other plate, which is graphene. So by putting positive voltage, we put some electrons, and by putting negative voltage, we put some holes here in the graphene. And by that, you can change the charge density in the graphene, and that way you can basically change the Fermi energy. So this is very beautiful knob in 2D materials, that you can change the Fermi energy just by applying a knob, which is voltage. So basically that is the thing we always routinely do. We basically make this kind of device, and we basically sit back in the lab and rotate this knob, which is called gate voltage, VBG, back gate voltage, and we measure resistance. And you can see in this case for graphene, the resistance is high at gate voltage, because at 0 gate voltage, Fermi energy is sitting at the meeting point of conduction and valence band, which is called Dirac point. So at Dirac point, you are getting high resistance, and if you go beyond the Dirac point toward electron side, which is positive, like positive gate voltage, or toward hole side, which is negative gate voltage, you have higher density of states or higher charge densities, so resistance decreases. So routinely we call this kind of curve as gating curve. Now, so this is up to now I have talked about simple graphene. Now like just at the beginning of the introduction, I talked like periodicity does some magic in system. So now you can induce external periodicity in graphene. So graphene already has some hexagonal pattern, so that is a lattice, and it has some band structure on based on that. But now what you can do, you can put some different kind of metals, and you can apply voltage. So if you lithographically make these metallic fingers, and you can basically create a periodic potential, which will affect give some effect on graphene. But lithographically you cannot there is a limitation of the scale, length scale you can achieve. One another way is to have Moira periodicity. So what you can do, you can take two graphene sheets and you can rotate one graphene sheet compared to the other, and in that case you can, from the picture you can see that you will get different kind of Moire structure, which is basically some beautiful pattern which change over the spatial direction. And if you change the twist angle, so the angle between these two sheets, we call it twist angle. So if you change the twist angle, this Moire pattern will also change, and the periodicity of Moire pattern will also change. So you have control over the length scale of the Moire periodicity, and you can actually achieve a length scale of 10 nanometer. So basically you have one lattice and you are putting external potential of 10 nanometer length scale. And beautiful thing is these two sheets are already obtained from nature, and nature is more perfect than us, so you will get sort of very perfect Moire potential. And of course they will change the band structure, and here I am explaining how the band structure is changing. So in first slide I told that periodicity can opens up some gap where the two energy dispersion curves are crossing each other. So in this case I am considering two graphenes on top of each other. So due to these two graphene sheets, you will have two cones of energy momentum dispersion, and they will be nearby depending on the twist angle. If you decrease the twist angle, they will be very nearby, and if your twist angle is 0, so they will basically be on top of each other. Now we can see that the energy dispersion relation of from these two sheets will cross each other, and of course there is some crosstalk between these two layers, and they will talk to each other, and you will have a gap. Now depending on the twist angle, so the energy scale associated in this crosstalk will change, and you may get very flat band. And that's what was the prediction in 2011. So this key person, who is Alan McDonald, along with his student Bistiger, they were playing with graphene. Like they probably did not have much to do, so they were theoretically taking two sheets and rotating them, and they were calculating the Hamiltonian. So at that time graphene, I think people did not know how to sort of rotate these things, and they were not sure whether they will really get this thing. So they are just playing. And what they find very surprisingly is that at a particular twist angle, the bands they are getting is very flat. So we can see one diagram of the band structure for a twist angle near 1.1 degree. That band, the central band has bandwidth of like something like 10 MeV, which is quite flat. That they called as magic angle. And so basically the physics is that at magic angle, you are getting very flat bands. And when you have flat bands, so flat bands, if that means that energy momentum dispersion is basically flat. And so from condensed matter knowledge, you know that you will not have much kinetic energy in the system. And since you don't have kinetic energy, so in the Hamiltonian, the electron correlation effect will dominate. So typically, in at least in our coursework, we always talk about kinetic energy, and in most of the cases we actually neglect the electron correlations. But in this flat band system, the kinetic energy is being coinced, whereas the electron correlation effect is dominating. And when electron correlations effect dominate, they give rise to different kind of novel physics, like Mott insulator, superconductivity, or ferromagnetism. So people then after I think almost 8 years, in 2018, some people find a way how to twist these graphene sheets, and they come up with a beautiful experimental result. One is this correlated insulation. So in the beginning slide, I explained that by gate voltage we can tune the charge density. So in this system, they have twisted bilayer graphene, and they are plotting conductance as a function of charge density. And this zero is basically the Dirac point. And you have flat band. So if you look at the band structure earlier, so this is higher band, this is higher band, and this is the flat band. So flat band is basically separated from higher conduction band or lower valence band by a gap, and in the gap you will have insulating state. So obviously that they will observe. So so that is corresponding to the charge density of ns, so minus ns and plus ns. So at minus ns and plus ns, conductance is really low because this is insulating state. But that is trivial, and we expect that. What they did not expect is that they are getting insulating state at half filling as well, at minus ns by 2 and plus ns by 2. So if you are sitting like right at the middle of the band, that means there you will expect the larger conductance. But in this case, they are actually getting insulating states, and that is basically correlated insulator, because that insulating state is coming from the correlation effect between electrons. So now the second thing they quickly observe is actually superconductivity. So they measure this conductance as a function of temperature and charge density. So basically in this plot, this is a color scale plot where resistance is being plotted. Blue means low resistance, and red or brown means high resistance. And they basically measured very low resistance state just near the correlated insulator state or insulating state, and that is basically the superconductivity. And that was sort of like that gave the boom in this field, and people start doing lots of measurement in this system. And another observation was ferromagnetism, and where basically at some charge density near 3/4 filling, people were observing some hysteresis in RXX. So basically, due to electron correlations in twisted bilayer, people are observing all sorts of novel states: correlated insulator, superconductivity, ferromagnetism, and whatnot. Because when you have correlations, you really don't know how to analyze the system, and exotic phenomena often occurs due to high electron correlations. Now, why it is interesting? Like you get superconductivity in graphene, but the TC is not super great. Like I think it has not crossed 10 Kelvin, so mostly it is around 1 Kelvin. So what is great about it? So one thing is people observe that this superconductivity has some similarity. Uh, yeah, this superconductivity has some similarity with cuprate. And in case of cuprate, if you dope the system, you get more insulated state. And in this case also, at some charge density you are getting superconductivity, and at other charge density you are getting correlated insulated state. So this is quite similar to cuprate superconductor. So people thought that if we analyze this graphene system, we probably might get some clue about the superconductivity. So the problem in superconductor physics is that there typically you have a sample, and if you want to dope the sample to study the effect of doping, you have to basically make a new sample. But in case of graphene, you just change the voltage and you are putting different charge density. So it is the same sample, everything is same, you are just changing the voltage and you are changing the conducting nature. So you can study superconductivity probably with more depth. And also all the exotic novel things are right next to each other, so that is a very interesting platform. So up to this, I was just explaining like brief overview of twisted bilayer graphene. I will now jump to our system, which is twisted double bilayer graphene. So if you have any question, I will briefly pause for 1 minute. Okay, I think everybody is understanding.
I'm interrupting you 1 second, Pratap. I think one of the participants has raised his hand. I guess it's Amit. So Akash, could you like unmute him and like we can get on with this question?
So we have a dedicated question answer session time after the talk. So we'll take the question that time only.
Actually, I prefer if I.
Okay, fine. Okay, fine. Yeah, Amit, go ahead.
Yeah, I have a question. Basically, I have two questions. One is regarding how it is guaranteed that twisting two graphenes layer will certainly develop periodicity. That is Moira sublattice that you are talking about.
Yeah.
And second question is the thing in the correlated insulator, the part that I should have a conductor in the middle part, that I have understood, but how from the correlation effect we actually getting an insulator, but it's not very clear to me.
Okay, so I think the first question I will answer in next few slides, and for the second question, so yeah, of course you expect high conductance at the middle of the bands, but when you are half filling and if you have high electron correlations, you can basically think is it as a Mott insulator. So it Mott insulator, what happens, you have basically state if like half filled, so at each side you have one electron, and since you have one electron, they will have a spin in one direction, so they will from Hund's rule they will not allow a second electron, because so from that you can see that the resistance that is sort of very stable configuration and resistance will be high. So this correlated insulator is also like Mott insulator state only, and the key is the electron-electron interaction. So if you have only kinetic energy or mostly kinetic energy, you can disregard this Hund's rule or electron-electron interaction a bit, and you can think that conductance will be really high. But when you have only electron-electron interaction at half filling, you will get this correlated insulator. So and I should mention that all these things are really not well understood yet. People are basically observing them in experiment, and theory people are also working side by side. So you can look at the papers which are like just 1 or 2 years old. So yeah, the bottom line is everything is not well understood, so people just speculate the way I am speculating. Yeah.
Okay, so Pratap, there is two questions from Dibba Shankar and Raghav Dhingra.
And I also think Surajit put forward a comment.
Yeah,
He wants to make a comment, I guess. So why don't we take his comment?
Yeah, I think he knows more in Mott insulator.
Okay, so Surajit, yeah, you can go ahead.
Yeah, but Pratap, actually the thing is, it will be much better that if you clear that what kind of a correlation are you talking about. Correlation is a big word. You should have been mentioned that what kind of it is a Coulomb potential, it is a spin-spin interaction. Otherwise, people will not understand what you are mean by the correlation. So that should be the clear in the Mott insulator phase. Otherwise, it is Mott insulator is well understood into the anti-ferromagnetism concept, where the two spin are aligned in the opposite direction, and because of that, in that case of the Coulomb potential nature, that you will get the insulating phase where electron cannot hop. This is the Omid. This is the simplest answer. Okay, for that.
Yeah. Thank you very much for illuminating this.
But Pratap, I have a surprisingly thing that you are just taking some minutes from you. There's the cuprate as a bigger puzzle is not about its dome. Bigger puzzle is a pseudogap phase. Does the twisted bilayer graphene has a pseudogap phase?
I think like very recent papers are trying to do some experiment in that regard, but uh,
And pseudogap
really
phase,
there is
does they
no
observe that wherever is a resistance
no
vanish and
no.
I
At least the paper I have read or
hmm.
explored so far, and they don't really talk about those details. I think this field is still new, at least in superconductivity.
One more thing, just to finish with it, you are talking about the much more time is the flat band, but does there evidence of the, I could have been expect from my the basic knowledge about that effective mass of electron. What is the effective mass of that electron here?
So I'll not give you effective mass of electron, but in next slides, actually our experiment will give some evidence that we are really
No,
seeing
but
some flat
that
band.
should have been
I will
reflected,
talk
isn't
about that
it? That
later.
effective mass has a relation with the inverse curvature of this band
Yeah, true.
structure.
So effective mass, like what effective mass you see in graphene, effective mass in twisted bilayer graphene is 10 times smaller. Sorry, either 10
10
or
times
100. I
smaller.
have forgot.
I should have
Sorry.
been
It will be
expect the
opposite.
higher because this
It will
as
be
much as
opposite.
this.
And from that they basically effective mass will have a role in the Fermi velocity as well, VF.
Okay.
Okay, so they basically measure Fermi velocity, and from that they can sort of measure the effective mass, or the
But
other
that
way.
is
I
a
have forgot.
indirect. I think direct where
No,
people have
no,
a D has oscillation. There one can
no,
measure
no, no,
directly. Huh?
no. I think from SDS oscillation they have not observed.
Huh. Okay. But this is
Subodhis
the more
can
direct
make
measurement if one
correct
can.
me.
Yeah.
Yeah, but there are many different ways, like you can measure VF, and from VF you can speculate the
No. The indirect
effective mass.
measurement, the measuring the Fermi velocity is creating much more error. I'm expecting a one quantity directly come out. If you measure that like density, people charge density, you are always prefer to measure Hall.
Yeah,
Because
yeah,
it has a direct quantities come out.
yeah,
Okay. Thanks, Pratap. Nice talk. Going on.
yeah. I know what you are talking about, the effective mass. Yeah, but yeah.
Okay, Pratap, Dibba Shankar wants to ask a question. Should we
Yeah,
take it now or later?
yeah. Sure. Go on.
Okay, Dibba Shankar, I have asked you to unmute.
Yeah, just one small question that in the Moira superlatives, if there is any translation, one graphene on the other, will the pattern will change or it will be conserved?
No. The pattern will not change.
Okay.
So like that is key for experiment as well. Like when we put the graphene, we cannot really align them in translation direction. That is random, and we still get same system.
Okay.
Yeah. So basically, you can take two sheets and you can actually twist them and change, give some translation. So by translation, so in a lattice, you can take any point as a center, right? And you can consider the lattice with respect to that. So translation will, in your mind, change the center only.
I see. Yeah, I understand.
The whole Moire picture will just translate.
Okay.
Yeah, Raghav.
So, Raghav, Raghav, now you can go ahead.
Yeah, hi. Really fun talk. I just had a small question. Correct me if I'm wrong. The E versus K band, it being flat, does it directly indicate that the electron interactions are more significant than the kinetic energy term? Because isn't that a function of like the total energy versus the crystal momentum, or is it just kinetic energy versus crystal momentum?
So you are right. So basically, in Hamiltonian, you have one kinetic energy term, and another one is this electron term, where the electron will have, let's say, different kind of interaction. One is this Coulomb interaction, as Sujit pointed out. Now, in condensed matter, we know that the velocity the momentum you can take as like some derivative of energy with respect to momentum that will give you the group velocity of the wave functions. And if you have energy momentum relation is really flat, that means this derivative is actually zero, and that sort of give the result that kinetic energy is really small in this system. So this is like very simplified picture to understand this, that kinetic energy will be lowered and electron correlation will effectively be larger. Does that answer your question? Or
Yeah, I think he is satisfied with
okay.
the answer. Okay, Pratap, you can go ahead now.
Okay, so let me move on now. So we take a different sort of device system, which is called twisted double bilayer graphene. In twisted bilayer graphene, people take graphene, monolayer graphene, and they twist that. But in our case, we take two bilayer graphenes and we put them on top of each other with a twist angle between them. So the fun part of bilayer graphene is that you can use electric field as a knob. For example, in bilayer graphene, if you have a perpendicular electric field, you can open up a gap, and gap is tunable with the electric field. And that electric field tunability is reflected in twisted double bilayer graphene as well. So there are already some paper out, including ours, where people have observed correlated states, and some people claim superconductivity as well, but the community overall believes that superconductivity is not still established in this system. So anyway, I will talk about what we found in this twisted double bilayer graphene system, and before that I briefly explain how we make these devices. So for making these devices, you basically need one microscope like this one, and in this microscope you can see that there is a bracket where we can put this small stage. So basically we have a stage in the microscope, we have another stage at the bottom, and using these two stages we can put different kind of 2D materials on top of each other. And for that you need two things. One is this glass slide kind of thing, which is called stamp. So on glass slides we make some stamp, which I will explain briefly later. And another thing is this bottle where you put some water so that you can sort of chill yourself, because you have to work for a long time to do this stacking. So basically for stacking you need like you exfoliate different kind of 2D materials. In this case we exfoliate graphene, which is bilayer graphene, and HBN. So basically we take graphite, small graphite crystals, and put them on scotch tape and put them on some silicon chip, and we look under the microscope whether we are lucky enough to get a bilayer graphene or not. Once we get bilayer graphene, we search similar way some HBN flakes, and then we do this stacking where we make the stamp first. In the stamp, as I showed earlier, which is a glass slide, on glass slide we put some PDMS, which is kind of some cushion, and on PDMS we have a PPC, which is a polymer which acts as a glue. And so now we put that stamp on the upper stage, and on the lower stage we put the silicon chip with BN on top of it. And we took the stamp close to the BN, we use heating also, and we basically pick up the HBN using this PPC glue. So now we have HBN picked up in the stamp. Then we take a different chip where we have the graphene, and we pick up graphene using the BN now. So between BN and graphene there is a high van der Waals force, because both the things are flat, and by that we pick up the HBN. So this way we pick up as many layers we want, and after that we drop this on another silicon substrate. So basically eventually from this individual 2D flakes we get these kind of stacks. Now in twisted bilayer or twisted double bilayer, one thing is you have two graphene layers which you have to align very perfectly. Like you have, so one stupid way is to check the crystal axis, but that will be overwhelming job. So what we do is we take a single graphene and we cut that graphene into two pieces. So that means we don't need to know what is the crystal axis. We just make sure that we are not randomly rotating our stage. So we have now two halves of graphene from same graphene, and now we pick one graphene at first, and then we rotate the lower stage where we have the other half, and we rotate with a precise angle, and then we pick up that graphene. So in this way, we are basically picking two halves of graphene from single graphene, and that way we really know that both these halves are actually aligned to each other with a precise angle. And I think there was one question. I think that question will be is answered here, like how we align these two graphenes. And in here I have put two realistic pictures. One is when we are picking up the first half, and second one is when we are picking up the second half as well. So this is the way we make the twisted bilayer graphene. But this cutting graphene is also not a trivial job, because you are working a micro scale, and you can not really take a knife from your kitchen and cut it. So basically, we have to take different approach, and this is one approach which we develop in our group, which is basically taking an optical fiber. So we take an optical fiber, we tapered it to form this kind of needle kind of structure, and with that we put that needle on top of glass slide, and we attach that with a tape, and we bend that needle, and using that needle now we can put that glass slide on the same microscope, and we can manipulate the stage, taking the needle near to the graphene, and we can cut the graphene into halves. So of course this is a fun job. So basically now we have stacks ready with twisted graphene or twisted double bilayer graphene sandwiched between two HBN. So these two HBNs will act as dielectric, because you need dielectric for putting the gate on top or on bottom. And also this dielectric, like this HBN acts as very good substrate for graphene system. So now you have stack, then you put some marker, and using lithography system you put the top gate, and then you shape the your stack into Hallberg geometry, and you put the leads again, doing some lithography and metal deposition, and finally you get the device. So this is the closer view of the device we get in this system, and these are two other images of the of other two devices. So now devices are ready. We are ready to do the measurement. And before that, I want to quickly mention what is challenge in this thing. So you of course get Moira potential when you have graphene on top of each other. But if you take image, you can see that the Moira potential is not always perfect. For example, if you look at this G panel, there you can see that Moira periodicity is quite like distorted. And in case of transport, like if you do ST measurement, probably they are a bit lucky because they can land their probe somewhere. But in transport, you are basically looking at the sample over a micron scale distance, because you will put some leads over micron scale, separated by a few microns. And so within that scale you need some sort of homogeneity in Moira potential. So you don't have much control here. So basically you make many devices, and either are lucky, or you do hard work to get that perfect device. So this is a hidden challenge in this electron transport, in particular in twisted bilayer graphene system. And there is another challenge which is true for I think any Indian physicists who are working some sort of frontier. So these are two recent papers published, like came to archive in same date, and one is talking about correlated Chern insulator in magic angle twisted bilayer graphene doing some spectroscopy, and another is talking about same physics doing some electron transport. So what is the case is that they really talk to each other, and they actually understand very quickly what is the new thing they are getting. So in our case, we made the twisted double bilayer graphene device actually quite earlier, when people were still thinking about twisted bilayer graphene, and we got some features, but we were not confident enough that what we are having, whether that is real or some artifacts, and suddenly some paper came out. So the point is they really collaborate and talk to each other before going to some conclusion, and whereas we sort of work sort of alone. So that is one challenge. Since the talk is sort of informal, I wanted to mention that. So now we have this device. So this is the cross section of the device, and we have silicon gate, highly doped silicon gate. We have SiO2 on top of that. Then we have HBN, then twisted double bilayer graphene, then another HBN, and on top of that you have the top gate. So using this bottom gate and top gate, I have already explained that we can change the charge density in the system. And another thing which we can tune is the electric field. So you have two voltage point, and you can imagine that using these two voltage, like these two top gates, you can tune the perpendicular electric field in this system. So I think I am quite late, so I'll be very quick. So in this system, this is a plot of resistance as a function of charge density in the x-axis and electric field in the y-axis. So what you are seeing here is plot of resistance. So red means high resistance and blue means low resistance. So if you look at the band structure side by side, so basically if you look at zero electric field, we are getting high resistance state at this two sides, which is charge density of minus 3.2 or and plus 3.2. So these are basically corresponding to the gap of between the flat band and the higher band, higher dispersive band. And now if you increase the electric field, you are reaching a point where the flat bands, which is marked by this pink color in the band structure, is splitting into two flat bands. And so there is another gap opening up between at the charge neutrality point, which is n equals to 0. And you you increase the electric field, one flat band is merging with the valence band, and other flat band is still there. And if you increase the electric field more, both the flat bands will merge with the dispersive band. So this is the basic electric field tunability of this system, and this is not there in twisted bilayer graphene. Now if you look closely enough, you will see other things like these cross-like features here, which is slightly high resistance resistive state, and there is another halo-like features, which is also another high resistive state. And those things you cannot explain from this kind of single particle calculation, and those are actually people think those are due to electron correlation. And you can actually see at this kind of electric field, and you can increase the parallel magnetic field, and now you can see that at half link the resistance is now increasing with parallel magnetic field. So that means the correlated gap here is actually increasing with the parallel magnetic field. So so then what we do, we did some systematic measurement of this single particle gaps. So basically we measure the resistance as a function of temperature at sitting at different electric field, and from it Arrhenius equation and extract the gap. So in this plot we are basically plotting the band gap as a function of electric field in this system. So we are measuring three different gaps. One is this minus ns gap and plus ns gap, and another one is this n equals to 0 gap. So in case of n equals to 0 gap, we see that band gap is increasing with the electric field magnitude, whereas gap at n equals to minus ns and plus ns are decreasing with the electric field. So basically we are quantifying the band gap, which we already observed from this resistance plot. Now here we are closely looking at one of these kind of plot, resistance versus temperature plot. So we can see there are different regimes. So first, this blue region where resistance is decreasing, which is basically insulating behavior, which we can explain that activated carriers are increasing and that's why resistance is decreasing, which is basically the Arrhenius activation between these two flat bands. Now there is this green region where suddenly the resistance is increasing with the temperature. So in some sense, this is basically insulated to metal transition, and that we can explain by the flatness of the band. So I think someone was asking how we can say that you have really flat band. So from this experiment, we will actually quantify the flatness of the band. So you can explain that since the band is flat, so this has some finite width. So even if you increase temperature infinitely, you don't have enough space to activate charge carriers, because after some point your band will end. So this width of band is actually giving this limit up to which you will get the metallic behavior, and beyond some point you will now activate charge carrier to the higher band, and now you will have again insulating behavior. So now what we do, we take this kind of curves and we theoretically try to feed this transition, insulated to metal transition, and from that we sort of get some quantitative information of the bandwidth. And in this right plot, I am plotting the bandwidth, what we get from this calculation as a function of electric field. And you can see that as you increase the electric field, the bandwidth is increasing. So, and then here we just explained that by using parallel magnetic field, we don't have much effect on the bandwidth. So from this work, we basically quantified the band gap and the bandwidth in this system. While band gap is not very like new thing, but bandwidth is quite new in our experiment. But because typically to do this kind of one estimation, you need to do spectroscopy or some RPS measurement. From electron transport, measuring bandwidth is really key thing in our work. So I have explained briefly the first work. Now I will quickly explain the second work, which is Perry curvature effect in twisted double bilayer graphene. So I told earlier that in graphene system we have basically two values. One is k and other one is this k prime value. And for these two values, actually Perry curvature is opposite. One is plus, another one is minus. So if you look at the electron dynamics, typically we ignore this term, this red term, and we typically take the count the effect of electric field and magnetic field. But if you compare, like if you include the Berry curvature term, and if you compare this two equation, you can see that Berry curvature is sort of acting like magnetic field, but not on k dot, but on r dot. Which like so, Berry curvature is like a magnetic field in real space. Sorry, momentum space. So like in real phase, magnetic field gives some deflection to electron. So similarly, Berry curvature also gives some deflection to the electron. And I told that in k and k prime value, the Berry curvature is actually opposite in sign. So that means the electrons from these two different values will get deflection in two different directions. So this is the device geometry, like measurement geometry. So you are sending some local current using two probes. So you are sending some electrons in one direction, and due to Berry curvature, electron like green like electrons, which is let's say from k values, are deflecting right side, and the blue like electrons are deflecting to the blue side. Now they will reach another probe which are sitting somewhat far away, which is called non-local probe. So there, so this effect is called valley Hall effect. There you will get an inverse effect, and you will get like a voltage drop. So here you are due to Berry curvature, you are getting valley current, but no charge current due to this electric field. In here in the non-local probe, you are getting voltage drop due to this valley current. So now you can measure this non-local voltage drop, and from that you can actually detect the Berry curvature physics, or yeah. So here I am plotting this local and non-local resistance as a function of charge density and the electric field. So in local plot, I have already I have shown to you earlier that we are getting this high resistance state due to gap, and we are also getting some correlated states, which is sort of kind of high resistance state. But in the non-local measurement, you can see that we are getting the single particle gap effect, but no correlation effect. So that is beautiful, because we in our calculation we see that Berry curvature hotspot, like where the Berry curvature is really high in the band structure, are sitting only near the band gap, not overall not at the whole band. So this is one proof that our non-local voltage is actually coming from the Berry curvature physics. Another proof is the magnitude itself. So if you do this kind of non-local measurement in any system, you will get ohmic contribution, which is basically if you put some current in some local probes and far away, you will also get some current, and you can calculate that current based on the geometry you have, and from that geometry you can calculate which we call ohmic contribution. So in the plot C, we are plotting line plots of this local, non-local resistance and ohmic contribution multiplied by 100, and you can see that non-local resistance, which is this cyan plot, the blue plot, is actually much higher than the green. and that means we are not getting ohmic contribution only, so something else is happening, and that give another proof that Berry curvature physics is playing some role here. And then we did some further analysis, like what type of valley current we are getting, and here we proved that the valley current we are getting is basically some diffusive valley transport. I'll not go into the details of this if you don't have any question. So at the end of this work, we basically proved that in twisted double bilayer graphene, you can get non-local voltage due to Berry curvature hotspot. And when you have Berry curvature in system, you expect non-trivial topology, and from that people expect different kind of breach physics. So in that sense, that is another novel observation in our work. So here is the summary. So basically, we are exploring twisted double bilayer graphene, and this system is highly electrically tunable, and all the gaps are electrically tunable, which we have proven by measuring the band gap, and then we measure the bandwidth also from the temperature dependence on the transport. We also shown some correlated gaps, and shown that that those correlated gaps are being enhanced by in-plane magnetic field. And finally, we demonstrated bulk valley transport measured by non-local resistance. So I will end my talk here. Now I will take questions. Yeah, Amit. Hello. Can someone unmute Amit? Or
Yeah, the thing that you are talking about, like electrons move in opposite direction. If the Berry curvature is opposite in two valleys, then I just want to know that is there something spin correlation or something like that in the initial stage of the electron, or they are completely uncorrelated in the notion of spin? I'm asking this because I just want to know that if there is something entanglement between these, just like the case in cross and reflection, is there
yeah.
something one-to-one analogy?
So when I was representing this band structure, one thing I should point it out is that here the band is actually degenerate. So when we are talking that there is one flat band, actually there are four flat bands due to fourfold degeneracy in graphene system. Two is from this two upspin and downspin, and another two is from this K valley and K prime valley. So for example, when I am talking about this red band in this system, actually you have four bands, four degenerate bands. Now let's come to this physics. So now from same band you have four type of electrons. Now when I am talking about valley transport, so you have to understand that for K valley we have both the spin flavor, and here we are not considering any spin effect because like we don't have magnetic field anyway. So when I am saying that K valley electrons are going to the left, that means some upspin electrons from K valley and some downspin electron from K valleys both are going in the left direction. So the bottom line is that this physics is still in spin degenerate case. And what you were talking about, so some people have observed spin Hall effect in some other system doing this kind of same non-local geometry, where spin effect comes into the picture, where valley degeneracy is not lifted. So spin Hall effect is still there, and probably someone can try to do some experiment to observe that. But in this case, we are actually observing valley Hall effect only.
I think Deepa Shankar has a question.
Yeah.
Yeah, so I couldn't actually understand the piezo response force microscopy measurement. So can you please explain that what experiment you actually doing?
Okay, so this is not from my experiment, I must say. So this is, I was saying, showing some images of actual Moira landscape. This is from some other group, so I don't really know much about this. But briefly, I think you have some stack where you don't put the top HBN. So you have top, for example, in this case, you have twisted BN. So you have two BNs on top of each other. You can have twisted bilayer graphene as well. And different people do different kind of microscopy. In this case, I think they basically use some AFM kind of
AFM
TIFF.
with some, okay.
Yeah, and there are some STM measurement as well, some TEM measurement as well. All of them give this kind of similar picture. But exactly in this case, what is the physics? I really don't remember.
No, but for your device, how you decide whether this
No,
would
that's the challenge. That's what I told in challenge part, that we really don't know in our device, because our device is anyway encapsulated with HBN, top
Right.
HBN as well. So you cannot go to, let's say we don't have this facility, but even if we have, we cannot do transport and this imaging simultaneously.
Okay, yeah.
So basically we depend on our luck factor, that what device we are getting, that is good enough. So only after doing measurement we come to know that the device is okay. Before that we really don't know that whether the Moira potential is really homogeneous enough or not.
I see. Yeah, another question is that when you are showing the sample picture, I saw there is different color. So
This one?
No. Previous slide probably. No, before that.
Sample picture.
13 slide.
This one?
Yeah, this B and C, they're different color. So if you intentionally put it, or it's there in your microscope?
So you see, it is actually color enhanced image. So basically, sometimes we cannot really see the graphene clearly just looking at the microscope. So we take the images and we play with the images, and so just to give, like, enhance the visibility of graphene here, we have changed the color, like played with the color. But
So,
actual color is something like this only.
No, for
greenish,
that,
bluish.
The slide number 13 here, these two pictures, B and C, these are through PDMS in transmission you are seeing, right?
Yeah, you are correct.
Yeah, okay. And another thing, that when you are picking up with PPC, in all your process, you actually pick up, but at the end, you stamp it on substrate. So how you decide to pick up or stamp it?
No. So we have to pick up everything, whatever we want to pick up. Let's say in twisted double bilayer graphene, we have BN at top, then bilayer graphene, then another bilayer graphene, and then the bottom BN.
Right.
So we have 4 2D materials.
Okay.
So all of them we will pick up using the PDMS. And after everything is being picked up, then only we will go to another blank SiO2 chip, where we'll just drop that stack. So we'll basically heat, and due to heating, PPC will melt.
Oh, so you will heat up. Okay.
Yeah. So whatever you want in our stack, we will just pick them.
So finally, when you are, transferring that compound sample on SiO2, you will heat up such that PPC melts and rotor.
Yeah. Okay. Yeah, you're right.
Okay, thanks.
I just wanted to mention that one thing you can imagine, that the top beam is actually seeing the PPC itself. So the top surface of HBN is actually not very great. So that's why we pick up every surface. Otherwise, you can at the bottom, middle, you can do another stack, and you can put one stack first, then you can put another stack. But that middle part will be polluted. So that's why we pick up everything first.
Okay, thanks.
Yeah.
Okay, I think there are 3 more hands. So I will ask to unmute one by one. First, Krishnendu Maji, Raghav Dhingra, and Surajit Datta. So Krishnendu, you can unmute yourself and ask the question.
Okay, so I have a question regarding the value Hall effect. So in case of value effect, do you see any edge state in the system?
Right.
Yeah, so how check that there are edge state in the system?
Yeah, so that was actually embedded in this slide, which I did not explain in great details. So basically, you are right that you will see valley Hall effect for both bulk and edge, and typically edge dominate at low temperature. And we analyzed our data at slightly elevated temperature. For example, our analysis were focused in this blue part, which is from, let's say, 40 Kelvin to 80 Kelvin. So there we expect bulk valley transport to dominate. And now the proof is this scaling factor. So in case of diffusive bulk transport, you will have a relation of RNL, non-local resistance, with the local resistance. So sigma xx is basically local conductance. And so basically, if you consider this equation, you will find that non-local resistance should be proportional to the cube of local resistance if the transport is bulk. And we really found that our non-local resistance is actually cubic. So in this plot E and F, we are plotting logarithm of RNL as a function of logarithm of RL, and we measure the slope to be 3 only. And from that we get the proof that the transport is diffusive through bulk. Now at lower temperature in this graph, for example, in this particular plot, 3 is increasing from this direction to that direction. So upper one is slightly lower temperature, and you can see that at lower temperature this slope is deviating from 3. So as I told earlier, that at low temperature edge transport will dominate. So we speculate that probably at low temperature we are getting some effect of edge transport, but of course we don't have like foolproof evidence. So you are right that at low temperature there will be edge transport as well.
Okay. Thank you.
Yeah, sure.
Okay, now Raghav, you can unmute yourself and ask the question.
Yeah. Could you go to the valley current setup again with the voltage? Yeah, I just wanted to confirm. So the twisted region is only between the probes. Is that correct?
So in this particular image, the full graphene is actually twisted. You have twisted graphene,
Yeah, so
and you are
why are we seeing the inverse effect specifically between the voltage where you've placed the voltage probe?
So you are saying that well, I have understood you are getting valley Hall effect here. Why should you get inverse valley Hall effect there, right? That's the question. Yeah. So the answer is that I think this. So answer is that if you look at this kind of paper, so they always explain the valley Hall effect using this Berry curvature physics, and then they say that if you get valley Hall effect, then of course you will get inverse valley Hall effect, and they don't really explain. So my intuition is that here some basic physics is coming into the picture, like this magnetic field and electric field thing, that if you have changing current that will induce magnetic field, similarly if you have magnetic field that will have opposite effect on electric current. So I think here also similar basic physics from electrodynamics will play a role, that if you get Hall effect due to current on voltage, you will get some sort of inverse Hall effect due to voltage on current. But to be honest, I don't have the actual like more broader answer.
That's okay. I'll just go through the publication.
Okay, so now Sujitda, you can unmute yourself.
Okay. So Pratap, I have one small question about the insulator and metal transition slide. That is, what is the lowest temperature you went?
Let me go to the slide. Yeah. So lowest
what is
temperature,
the lowest temperature you went?
I think we went up to 300 millikelvin. 300 millikelvin. But
okay,
in
so,
this, just 1 minute. In this plot, I think I have chopped off this lowest temperature part. Probably we are plotting up to 10 Kelvin only, or 5 Kelvin.
So I think that fitting you are showing, that where from you RNS activation you are showing, I think it is better to plot in a logger versus inverse temperature. This fitting is I don't know what is the least square value. It's not looks good, that range you are showing.
Yeah,
like
right.
Green one, it is clearly deviating as I go to the low temperature limit. So I believe that if you plot in the logger versus inverse temperature, that should be the come out to the linear scale. That is the linear fitting one should show.
So we
to be honest,
we use that approach to like to basically
at least for
analyze
the
this
low
part.
temperature 20 Kelvin up to, say, let's say 10 millikelvin to 20 Kelvin, or whatever, the 300 millikelvin to 20 Kelvin.
So you are right.
But
So
this is the,
you are right. So here in this blue region, where the drop in resistance is actually drastic, so which is sort
yeah,
of
so that's why the log scale is the good fit, because exponentially you can suppress many things. I can show you a fitting in the exponential range where you can fit it easily, but if you plot in a log scale, this is a higher activation, means your resistance is increment, I think, 4 factor. Yeah, so
yeah.
almost like a 4 factor.
Let me
And
answer first.
second thing, that how you are sure that it is from the insulator to metal transition? Why you are calling it a metal?
So let me answer first.
Hmm.
So you are right that in the blue region, the resistance is actually dropping sort of exponentially, and that's where we extract the band gap, and that's where we actually take
No, but
logarithmic scale and
it
fit.
is not clear that it is exponential, because it's 4 factor, that is okay. But in the fitting, I don't see that it is well fitted in exponentially. But that's okay if you claim it. But I am saying that if you do it in the log R versus inverse temperature, that will be the more clear that it is really following the exponential or not. 23,
So that's
the 25 number slide. Yeah.
So that's what I'm going to say, that
Hmm.
when we look at this blue region, so
Hmm.
we actually go to lower temperature as well, and there we really fit using the exponential logarithm plot. But when we look at this cropped section, which is the insulated to metal transition, there we
Yeah.
fit this equation, and we have actually played with fitting. And to be honest, if you follow like more, go to lower part, you cannot, like, this fitting curve will not follow the actual experimental data. So the like final answer is that the fitting is not super great. But the thing is, as I pointed out, the novelty is that uh, anybody have not tried ever to get quantitative information about bandwidth from this kind of electron transport. So you may do a bad fitting, but at least that gives some clue of the quantitative
What
information.
is the
So
error
your
bar in
point
the
is,
bandwidth if somebody asks in the
so that's
transport?
what I'm just going to say, that your point will be well taken when you consider this error bar, and you can see that error is not very small. They are quite substantial. For example, this point error is quite large. So yeah, you are
Yeah, but
right that
the another thing is that, Pratap, does someone has tried to known thing like one measure in the transport versus spectroscopy measurement? Does anybody try that to compare it, that how much one can reliable on the transport? Let's just say that, like, if I
yeah
measure some quantity from the transport and do the spectroscopy, how
yeah
much I am away from it? Is there
so
any paper or something?
so that's true. So in twisted alveolar graphene, in actually our papers are actually I think second first published paper. So still the field is actually like at its earlier stage, and I have not seen any other type of spectroscopy paper which quantify this bandwidth.
I
But
see.
from theoretical calculation, people speculate that will be in the order of 10 MeV, as I told earlier.
10.
Yeah,
Okay.
so that's where the point is, like of course you can say that I don't have good fitting, so I don't have anything to say or anything to believe from this. But at least you go one step further by doing this kind of
Yeah, but this okay, but if you one can try something, give the one can extra
yeah.
quantity, but that is always welcome, because there's nothing to be.
And
But
of course,
Pratap,
as a scientist, you have some, yes.
so Pratap, that thing you were talking about, there's an answer. There's just a I think someone, I forget his name. In that case, oh yeah, Amit's question, that is there is a mixture of the spin. So what happened if somebody applied the magnetic field? Does the spin degeneracy lifted? It is come out.
Well,
Though you
well,
are
well.
not showing, but I'm just asking.
Well. Yeah, you are asking question in right direction. So
Valley,
there are,
valley,
so
valley, valley current. That Amit has asked now, there
yeah,
is any spin entanglement or not. So as you explained that there is a fourfold degeneracy. So two valley has a two upspin and two downspin. So they will have a give a current of the mixed spin. So if I apply magnetic field, the spin degeneracy should be lifted.
yeah. So let me answer this question. So this is actually very sort of interesting question which our community is trying to solve. So basically, in this parameter space, you have fourfold degenerate bands, and as Amit was saying that you can leave the degeneracy if you apply some, let's say, magnetic field. So basically, you will leave the degeneracy in this fourth space. So not necessarily you will get upspin, downspin. You can get some state which is sort of, in his language, is entangled between upspin or downspin. So all I mean, in the four-dimensional Hilbert space, you can get four degeneracy lifted state in any direction. Now question is how to know
Hello.
what is the exact thing is going on, and for that you apply magnetic field. In this case we are applying parallel magnetic field, and you can see that the gap is increasing with the parallel magnetic field. So gap, when you have a gap at the half filling, that means you are already lifting one degeneracy. You don't know whether this is between spin or valley. Now question is whether with magnetic field that gap is increasing or decreasing, or it is unchanged. So in this case it is increasing, and from that the evolution of gap as a function of magnetic field, you can say whether that is spin polarized or valley polarized. Now the thing is, of course, in twisted double bilayer graphene there are not too many experiments. In twisted bilayer graphene there are already some experiments, but most of the paper they speculate that the fast degeneracy lifting is giving spin polarized state, but still there are doubts. So basically what you do, you fit this gap as a function of magnetic field, and you take the proportionality constant, which is the G factor or something like that, and from that value of G factor you speculate. If it is like close to 2, you think that Zeeman splitting kind of physics is going on, and you are seeing spin polarized state, whereas it is something different, then you speculate that valley polarization is happening. So yeah, so that kind of measurement are going on, and people are trying to understand this thing.
So when G is 2, why should I expect the Z? G is 2 means it is a spin. It is always there. It is a
Yeah, so
natural
that's what I'm saying.
quantity.
When your G is
So
2, then you expect that spin polarization is going on, and when G is something else, you think probably valley polarization is going on.
Okay, so I think Surajita,
thank you, Pratap. Nice talk.
yeah, you
Yeah,
guys
thank you,
can
thank you.
continue this discussion later, and I think there is no more questions. So yeah, it was a very wonderful talk, Pratapda, and it was very interactive. So yeah, we want the talks to be like this only, so that the participants interact a lot, and that was the main motto of this organizing this talk. So yeah, thank you again for giving this talk, and thank you all the participants for participating. So okay, so we'll stop the meeting now. Yeah.
Yeah, thank you, yes.